is your book assignment. I'm sorry, I don't know what happened on my gold sheet. I think I know what happened. I think last year we got short on time. Is maybe what happened. But that's your book assignment. We're gonna go through what optimization is today. If you look, we have like 3 days to figure out optimization. Okay, usually it's like a day or two on a section. We've got 3 days, and then we have a quiz on it. Okay, and then we have related rates for 3 days, and then we have a quiz on it. And then we have a couple tiny sections, and then our test. We will start the concept of antiderivatives before we go into our finals, but it kind of helps with that process. And then your final, this is like your second to last final. Your final is Friday morning for this class. So, but this is it. So I'll get your tests graded this weekend. We'll get them back on Monday, and we'll have 1 test, 2 quizzes, and a final left to put in the grade book. Okay? Just kind of wrap your mind around that. Okay? So, don't get out your notes quite yet. Okay? What I want you to do is I want you to read through. Oh, I'm not, like, hooked in. That would help. Apparently we're slow today here. Okay, I would like you to read through this example. Just read through it. Okay, what are your thoughts? You miss Toys R Us? Yeah. Boxes R Us doesn't sound very exciting. The container store. Okay. Let's take this last line. How large should we cut the squares to make the box with as large a volume as possible? Give me a synonym for as large. Maximum. Have we been doing things with maximums and minimums? Just every once in a while, right? Okay. Like we have these tests for maximums and minimums, right? Do you think we could use calculus to find the maximum volume of this box? That's what we're going to do, okay? How would we make the equation, Dylan asks? Well, lucky for you. What'd you say? The derivative of the volume equation. Yeah. Okay? If I'm asking you for a maximum, it probably deals with the derivative. I think it's just. I think we just like that. Kind of like the bottom of the box. Right? Okay. So here's what's going to happen. We probably have to do something with the derivative. And in this particular case, it's probably going to deal with the volume, right? So how do we put all these pieces together in order to be able to know that it's the volume and we take the derivative and how do we go from there, okay? So these are my expectations when we put it all together, okay? We know we're going to need a derivative to find our maximum. What I want you to do first, though, okay, because we were talking about like this sheet of cardboard and we're making it into a box by cutting squares. You should probably draw a picture so you can get an idea of what's happening. And this is what's at the top of your, it's not a free body.
Yeah, don't we know?
What? These are way better than free body
Good.
diagrams. There's no movement involved in these, right? Okay. So draw a picture so you can make some labels. You'll probably have to define a variable or two. Okay? And when I say two, you're going to have a primary equation. In the example that we just read through, we want to maximize the volume. So our volume is going to be our primary equation. However, if there are two different variables, do you know how to take derivatives and find maximums and minimums with two different variables? I mean, you have y equals something with x, right? But have we ever had like more than one variable thrown in there? It's always just been x, okay? So if there are potentially two variables in your primary equation, you need a secondary equation so we can make some substitutions and only be left with one variable, okay? From there, what are you trying to optimize, okay? That is what your primary equation needs to deal with, okay? You'll want to think about what the domain is, okay? That will impact how you find your maximum. Okay? If we have, a tangible item like a piece of cardboard, if our cardboard is 12 by 12, can I cut 7 by 7 squares out of the corners? No, I'm running out of cardboard, right? There's not enough cardboard, okay? So we have to think about those things so that when we get down to the derivative, we don't test critical points that aren't going to work, okay? In terms of the tangible aspect of our problem, okay? Algebra works all the time, but if we're talking about something tangible, we can't have like negative area or negative length, okay? Then we'll use the first derivative test just so you don't have to use the second derivative, okay? But we'll use the first derivative test to find the minimum and maximum. Now, what is something that I like to see when you use the first derivative test? How do you tell something's a minimum or a maximum? Oh, your number line, and you can see the change in derivative, okay? That is something that I will need to see. Don't just assume that the answer you get is for sure the maximum. Like if you only get one critical point, you still need to make sure it's your maximum or minimum depending on the problem, because maybe you messed up somewhere and it will tell you that, okay? So, let's go back to our problem number 1 and do these steps to solve the problem, okay? Now, in problem number 1, we won't have to worry about a secondary equation, but I'll show you what that looks like here pretty soon, okay? All right. So we have a 12 by 12 piece of cardboard, right? Let's draw that. Okay. And what are we doing to this piece of cardboard? How so? What are we cutting out of it? Okay, 4 congruent squares at the corner, right? Do we know how big those squares are? No. So I'm going to say that they're x by x squares. I don't know what they are. Okay. Your primary equation, and if you need to make a note of this on your note sheet, your primary equation is always going to connect to what you're trying to maximize or minimize. So it says we are trying to maximize our volume. Our primary equation better be about volume. Okay? So our volume How do we find the volume of a box? Length times width times height. Okay, I'll ask you the easy one first. What's the height of our box once we cut these squares and we fold them up? Okay, yeah, if we cut these squares and we fold up, we have a height of x, right? That's our height. Now, this is a square box, so our length and width are going to be the same. Once we cut these and fold them up, what is the length of each side of our box? 12 minus 2x. Yeah. So maybe we want to write this. Our volume is 12 minus 2x, the quantity squared, times x. Now, since we only have x as a variable, we do not need a secondary equation. We would only need a secondary equation if our volume equation involved an x and a y. I'll show you one like that in number 2. Okay, so once we have our equation set up and we want to find the maximum, what do we need to do? Find the derivative. We need to use our first derivative test. Now, here's where you have options, right? You can choose to multiply this all out and use the power rule 3 times, or we can use the product rule. What would you like to do? Do the product rule? Okay, let's do it. So our product rule, so volume derivative would be 2 times 12 minus 2x to the first power times negative 2 times x. Plus 12 minus 2x, this quantity squared, times 1. Okay, well, we have our derivative. Ooh, I skipped something. Can we take a pause and go back? I get so excited about taking the derivative. We didn't talk about the domain. What's the smallest we can cut our squares? I mean, we could cut like no squares, right? And we're not going to do that, but x probably has to be positive, right? What's the biggest we would cut our squares? 6. All right, so x better be between 0 and 6. It's possible that our algebra could lead us to numbers outside of that domain. We need to ignore them because they don't make sense to our problem. Okay? Okay, so back to our first derivative test. We took our derivative, and now we're going to have to find our critical points, right? So we need to know where our derivative is 0. Well, in order to know where our derivative is 0, we're going to have to do some algebra, right? So what happens when we take 2 times 12 minus 2x times negative 2 times x? Can we do all of that distribution all at once? Can we do that? Is that okay? What is 2 times negative 2 times x? Negative 4x is what we're distributing through. So what is negative 4x times 12? And negative 4x times negative 2x. Because we're multiplying. Okay. And you can have a calculator. And then 12 minus 2x, the quantity squared. We thought we'd try to get out of having to do that, but we have to do it anyway in our derivative. Okay? So I know that when I square a binomial, we get that a squared plus 2ab plus b squared. When we combine like terms, what do we get? 12x squared minus, is that 96x plus 144. Okay, we're finally to the point where we can start doing some solving here for x. Okay, now lucky for you, you will have a calculator. But in order to factor this, what should we do first? Okay, let's factor out a 12. And when we factor out a 12, we're left with x squared minus 8x plus 12. Oh, and what is this factor to?
X minus 6.
Thank you, Ellen. Did you think I said
you
even?
asked Owen?
Yeah, I did. That's okay. We'll take you. Okay. Owen will get a shot next.
Owen is a shot. I crushed your chance.
Owen, what are our critical points?
6 and 2.
And what should we do with those critical points?
Put them on a number.
Put them on a number line. Okay. Now, technically, 2's the only one that is in our domain. I mean, we're not going to create a box by cutting out 6 by 6 squares, right? Okay. So, some of us are going to get excited and be like, yep, 2's it. That's what we're going to use. It's done. But if you don't actually show me that it is the maximum on your number line, I'm going to take off points. I'll be very clear. Okay? I need you to actually follow through and make sure that it is the maximum. So, when I plug in 0, we would get a positive value. And when we plug in like 3, and like, let's be smart about this. Don't come up to here and try to plug in 3 and figure out what that is. If I plug 3 in here, this is positive, this would be negative, this would be positive. We'd have a negative product, right? I'm not even going to like come over here to the other side of 6. It doesn't matter. 6 cannot be our answer. But we've already found a maximum, right? At x equals 2, our derivative changes from positive to negative. We have a maximum. Now, you don't have to like, tell me that the derivative changes from positive to negative. There's no justifying that you need to do. But we found our maximum. Okay? At this point, it comes back to the question. Okay? How do we need to answer the question? How large should the cut squares be? What's the answer to that question?
2 inches.
2 inches by 2 inches. That would be the answer I would look for. Isn't it nice to actually do something with the first derivative test that means something? Like people do this in real life, right? Wouldn't maximum volume of a box be important for a boxing company? Okay. So we actually we finally get to do something that you can see has benefit. Okay? Which I know a lot of you have been waiting for. Okay? Finally in there. So both this and then next week the section that we learn, is it next week? Yeah. Related rates. Both of those are very hands-on examples about how calculus is used. Okay? Go ahead and read through the second one. Okay. So we've got a piece of paper, right? What are we trying to optimize? Okay. And do we want maximum or minimum? Okay, it says least amount of paper is used, right? So we are trying to minimize, and we are trying to minimize, like, basically like the area that we have print on, right? Is that what's happening? Or the size of the paper, I guess, right? Because we know we want 24 square inches of print. It's more about the size of the paper. We want the smallest piece of paper possible. That was a lot of pieces. Okay. So, what do we know? We have a piece of paper. And it's a rectangle. Right? Ooh. The margins on each side should be 1. And the margins, top and bottom, should be 1.5. Okay. What do we know about this right here? Okay, that right there is 24 square inches. Okay. We need to figure out how big this piece of paper is. Okay. So we need to figure out 2 dimensions, right? Okay. What I'm going to do, I'm going to call this dimension X and this dimension Y, so that we can identify that X times Y is 24. Do you agree with that? Okay. Does the area of the inside of our paper have anything to do with the overall dimensions? Okay. That really doesn't directly connect to what we're trying to minimize, okay? So this is called our secondary equation. Because it doesn't have to do with the dimensions, and it like equals a number, okay? That is what we put off to the side for our secondary equation. Our primary equation is the area of our piece of paper. Because we're talking about the least amount used, okay? Well, what would the dimensions of our piece of paper be?
Y plus 3 and X plus 2.
Okay, X plus 2 and Y plus 3. So the area in which we are trying to minimize would be X plus 2 times Y plus 3. Okay, so let's take a moment and look at primary versus secondary. Primary, we are trying to minimize the dimensions of our piece of paper. Okay, so notice how I have I choose A for area. Last time I chose V for volume. It's kind of like our Y equals, right? And then I have our area here. On our secondary equation, we have the same 2 variables, but we have a numeric value as a part of that equation. Okay, do you see the difference in how they look? Where this one has like the 2 variables with a numeric value. This has the 2 variables with whatever we're trying to optimize. Okay, what we have to do, because we can't use the first derivative test on something that looks like this, because we want to take the derivative respect of 1 variable. Okay, so we can use our secondary equation and make this only have one variable? Does it matter which one you choose? It sure does not, okay? Some of us may solve for y, some of us may solve for x. We're still going to get to the same answer eventually, okay? What would you like to solve for in this equation? I'll let you be the leader here. You want to solve for x? So x equals 24 divided by y. I like this. This gives us a chance to do a derivative with y instead of x. Okay. So x is 24 over y. So we're going to go ahead and substitute that in. Okay. And let's go ahead and just take a different approach today. Let's go ahead and multiply out, or from the last problem. Last problem we took the product rule, right? Let's just, to see how it's different, let's go ahead and multiply all the way out and then take the derivative. Okay, so help me out with our foiling here. What's 24 over y times y? 24 over y times 3. Is that 72 over y? Yes? No? Okay. Plus 2 times y plus 6. Okay, so now we need our derivative, so we can use the first derivative test. Well, really, do we care about 24 and 6? No, their derivatives are 0, okay? How about 72 over y? Okay, so this is 72 y to the negative first, so our derivative is negative 1 times 72 y to the negative second, right? Okay. Now remember, for our first derivative test, we do need to find where our derivative is both 0 and undefined. And since we have a negative exponent, it's going to be important for us to utilize that so we can find both. So when we set this equal to 0, this is negative 72 over y squared. Okay. So we're going to need to make common denominators in order for us to be able to figure out what? Yeah. We'll talk about the domain at the end. How's that? Thank you. So we have negative 72 plus y squared all over y squared. 2, there's a 2. Sorry. Okay, so our critical points. Where's our denominator? 0. Okay. And where is our numerator? 0. Plus or minus 6? All right, people. Whoops. Negative 6. Is that going to be a dimension of where the print is? No. So we don't care about negative 6. Put it on your number line just so you don't choose a number not in the interval, but don't test that interval. Okay? Really, you don't need to test the other side of 0. Well, let's do it just in case. If we plug in a negative number, a negative number. If we plug in a number between 0 and 6, And how about on the other side of 6? Hey! Just like we wanted, right? We want a minimum. So y equals 6 gives us our minimum. So y equals 6, that's just my answer. First of all, I need a dimension, right? We had 2 variables to begin with. So we know that y equals 6 gives us a maximum, which means x is what? X is 4. However, x and y don't represent the dimensions of our piece of paper. X and y represented the dimensions where the print was. The dimensions of our piece of paper were x plus, was it 2?
Yeah.
X plus 2 and y plus 3. So the dimensions of our piece of paper are actually 6 inches by 9 inches. Okay, questions about that one? Okay, really, we're not doing anything different than what we did when we did the first derivative test last unit. We're just actually applying it to something that has a meaning. Okay, so I didn't talk about the official domain at the beginning. Okay. Once again, I got going, but when we got to here, we knew okay, -6 is not going to be there, so I'm not going to test it. And so thinking about it, if you forget to think about it at the beginning, at least think about it when you're here on the number line, so that you don't do more work than what's necessary, or you don't accidentally identify something that shouldn't be in the middle. I am not going to take off points for not writing down the domain. It's something you need to think about. Okay. All right. Oh, we're in here till 40, right? I was thinking 4th hour and 35, and okay, we have time for our third example. Okay, go ahead and read our last example on the back. What?
So it's just a job, it's not a daily job.
Just a job. Go with it.
I know what I want. I'm changing my careers. I want to be a surgeon anymore.
Okay, really? This is just a fancy way of me saying I want you to take 4 minus x squared and find the coordinate on 4 minus x squared. That's the closest to the coordinate 0, 2. I just put a level there to make it okay. All right, we have a parabola and we have a coordinate, and I want to find closest points on the parabola to the coordinate. Now, why do I say points? It's going to be 2 because we have some symmetry, right? That coordinate that we're trying to get closest to is in the mid. It's on the axis of symmetry, so we're probably going to get 2 answers out of this. Unless it's the vertex, we'd only get 1. Okay. So if I want the closest point, what do we? Okay, we're trying to minimize what?
Distance.
Ooh, the distance. Okay, so we have some random coordinate xy, and I want to minimize the distance. So our primary equation has to deal with the distance between point xy and point 0,2. It's always disappointing to hear that the distance will minimize for what? Okay, we are trying to minimize the distance from one of those coordinates on the parabola to point 0,2. Okay, now, the domain for this problem, we're looking for coordinates on a parabola. Anything goes, right? We can have negative x's, we can have positive x's. Okay, so the domain's all real numbers here. Can we use the first derivative test on this? No. Which means we need a secondary equation so that we can write this equation in terms of one variable. What is our secondary equation? There's something we know about that parabola. Well, but that's just a number. I need an equation. We know that y equals 4 minus x squared. Look at that. Okay, so you can do some different things with your substitution. But we know that x minus 0 squared is x squared. And we know from over here y is 4 minus x squared. So we can take our 4 minus x squared and throw it in for y. And so now our equation for the distance only involves x's. Could I write this as 2 minus x squared instead? Okay. And there's really no way of getting around it. We have to multiply out that binomial. So 2 minus x squared, the quantity squared, would give us 4 minus 4x squared plus x to the 4th. So what we have is the square root of x to the 4th minus 3x squared plus 4. Okay, now, if I asked you to do the first derivative test on this equation, you would have to have the derivative of that radical and use the chain rule, right? Now let's think about this. If I am minimizing a square root, isn't it really like the inside that we want to minimize? Because when we take the square root of it, it's still going to be small. So I will let you find the minimum of x to the 4th minus 3x squared plus 4 so that you don't have to worry about doing the radical in your derivative. Because if we minimize this, then we're minimizing the square root of it, okay? Is that okay? I mean, it's less work, right? Okay, take that derivative and find me the critical points. Julia, what's your derivative?
4x to the third minus 6x.
And when you found your critical points by setting it equal to 0, what'd you get?
0 and then plus a negative radical 3/2.
Not pretty, but that's what it is. Right? We have to factor out a 2x. Left over is 2x squared minus 3. Okay? So let's put those on a number line. Okay, remember we talked about how really we could have anything for our answer because we're talking about coordinates on a parabola. We can have positives, we can have negatives. Okay, anything goes. Here's our number line that we have to figure out. Now, radical 3/2. 3/2, a little bit more than 1, but the square root of it, you have a calculator, so it can help you. Yeah, we're running a little short on time, I'll just tell you. There's our number line. Okay, so we were trying to find our what? So where do we have minimums at? Here and here. So our two coordinates that are the closest to the coordinate 0, 2 is negative radical 3/2, comma something, and radical 3/2, comma something. How do I figure out what the y coordinate is? Go back to the secondary equation. The secondary equation is there for you to find the second variable. We have 4 minus x squared. If we plug in positive or negative radical 3/2, what do we get for y? 5/2? So there are our two coordinates that are the closest. Yay! Okay. Do what you can on your homework this weekend. We have all day Monday to figure out kind of what went well, what didn't. We'll do a little damage control, okay? But I need you to attempt every problem. Okay? Okay.